right. So we ended up last time with this. No, in fact, let me rewind a bit. Last time we've seen that there exists such a thing as incompressible strings. So by a counting argument, we could see that despite the fact that I didn't exhibit an n-bit string that is incompressible, namely that its shortest program is as long as its length, we could see that they need to exist. And what's one thing we did. And then we ended up with some list of problems with plain complexity. Can you remember what the problems were? One of them had to do with the chain rule.
The chain rule had a logarithmic additive factor rather than a constant one. Right?
Yeah, exactly. We had a sort of awkward order of log of c of xy as an error term. We thought it could be fun to get rid of it and get O of 1 as we can get in algorithmic complexity in the best case. We also saw some very informal thing that, we have some strings, if you take an n-bit string which is completely random and you also take n to be random, it feels like this string is carrying two pieces of information with it. It's carrying the randomness in its length, and it's carrying the randomness within it. And so I said, maybe a more natural upper bound would be n, the length of the string. So the natural upper bound for its algorithmic complexity would be the algorithmic complexity within the bits, so n, plus the algorithmic complexity of its length, because it's also carrying that, which was my n in my example. And finally, we saw a very serious one, which was Solomonov's program. He defined a measure, which was a very intuitive measure. You sum over all programs that can compute a string x, not just the short one, all of them. 2 to the minus the length of that program. And that corresponded basically into the idea of putting a monkey in front of a universal computer, which was typing bits at random. So he has a chance, 2 to the minus L, of writing down an L-bit long program. So you sum over all those programs. And it seems like it would be a nice measure for x. But we've seen that with plain complexity, the framework in which we work, P of x was infinite for all x. So just this sum was blowing up, which is somewhat annoying because it seems like, at least intuitively, there's actually a well-defined notion of putting a monkey in front of a computer, giving him a chance 1/2 of typing 0, 1/2 of typing 1, and that should be, giving a finite probability that he types a program yielding the computation for x. That was our last problem with plain complexity. In fact, even before starting the new section, I'm going to add one more. 4. And I recall old school stuff that we did together. Recalling coding theory. That could be a fun code. I call it SP for shortest program. A code from 0, 1 star to 0, 1 star. Now we're coding bit strings into other bit strings. We've seen various examples of such codes. And what's SP doing? Well, it's mapping x, the string x, to its shortest program, x star. Now please don't be confused, I'm using the star in various contexts. The star here in 0, 1 star means the set of all finite bit strings. Whereas the star here is for x star, it means the shortest program for x. Right? It seems to be like a natural code to define. We have a bit string and we map it to its shortest program. We know it could be decoded by taking a universal computer, running x star on the universal computer, and expanding x star back into x. So this thing, SP, is a natural code. But when we studied coding theory, one key concept that we right away found was the notion of a prefix code. So let me just ask, is it a prefix code? No, it's not. In fact, if we consider for y different than x, consider 2-bit strings y and x different, nothing prevents y star from being a prefix of x star. A prefix, just to remind you, it means that if y star is a prefix of x star, it means that x star starts with y star and some other string. If we would say, okay, y star is a prefix of x star. And why is that? Well, because a priori, nothing prevents a program which is, in our example, a potential code word, from being the prefix of another program.
Okay, I might even have an example. If you consider all this, fix an encoding and then consider all the strings that are incompressible, whose shortest program is just print the string. And then if we imagine that in our encoding, the print part of that program is the first like 10 bits or something, then like print, I don't know, some string may be a prefix for print a longer string where the first string is like contained within it. You see what I mean?
No, sorry, can you repeat?
Okay, imagine you're just doing programs that are like print and then a long string that you want to print.
Yeah.
For simplicity, just imagine the string is just all zeros.
Yeah.
And then the print section of your code may be repeated many times.
Within the string.
Like, okay, say the print section is, I don't know, this particular string X or whatever. Then there could be many incompressible strings whose shortest program is just print the string. And if one of those strings is a prefix of another one,
okay,
then one of the print programs will be a prefix of the other one because they're the same program. They just have print and then the string.
Yeah. So print is like some routine that you're using in different cases. You know, print X, maybe print Y, or maybe print X and some other stuff. And then the print X and some other stuff has as a prefix the print X program.
Yeah, basically, because in this particular encoding, the print is always the first piece. And then so for all the incompressible strings, it's always the print string.
Yeah. Yeah, I understand the example. Yeah, I think it's, in fact, I'm invoking a very general argument. A priori, nothing prevents a program from being a prefix of another program. So it might be that the shortest program X star or Y star is a prefix of the shortest program X star. So maybe with that example, we can perhaps more easily see the solution or the motivation and the formalization of prefix complexity. What we're going to impose is, after the because, I wrote down nothing prevents a program from being the prefix of another program. we're going to demand that all valid programs form a prefix-free set. No halting program will be the prefix of another halting program. So by imposing the latter restriction, we define prefix complexity. Well, we eventually define, but let me just write it anyways. We define prefix complexity and solve problems one, two, 3, and 4. I'm referring to the list that started last time. 1, 2, 3, and 4 is this item here. Questions? Don't worry, I'm going to expand on what we're doing here. That's basically the topic of today's lecture. To define formally, properly, prefix complexity. Absent any question? Prefix complexity. In the setting of prefix complexity, letter like this, it's like this. It is demanded that a program must be self-delimited. Namely, its total length in bits must be given in the program itself. For Turing machines, it means that the head scanning the program is not allowed to overshoot. So just to anticipate a little bit, we had, we're going to be formalizing so-called self-delimiting Turing machines. I'm still having a more of a general discussion here, but to anticipate a little bit the formalism, the program will be given on a read-only tape. It can only read. And then it has a work tape on which it can do some stuff. You know, the way we define Turing machines in the course, we said that there's only one tape, so the program sits on it, and then the Turing machine manipulates the program, the bits within the program, and ends up with a computation. But now we're going to have a read-only tape. It's going to only read the bits of the program, and it's going to have a work tape on which it can do stuff, to compute things. But prior to imposing self-delimitation of programs, our programs were sort of allowed a little cheat. Because the alphabet of program, the alphabet of the input, was it really binary? You know, the input could read a 0 and a 1, interpreting as the first bit of the program, moving the head, 0 or 1, interpreting as another bit of the program. But eventually, it could hit the first blank. And it could say, oh yeah, I'm hitting a blank, so my program is done. And so we didn't have to care about making sure that the program sitting on the Turing machine was self-delimited. The information about its own length was contained within itself. Because it could cheat, it could overshoot, hit the blank, and realize, okay, that's the end of my program, so my program is this long. Here we're going to be asking that the program is given on a read-only tape. And not only that, but I guess I need to do that. The read-only tape can only move to the right, never back, and it is not allowed to read a blank. So it only can read bits. So we're definitely not cheating with an implicit ternary alphabet, like we were when we had programs being bits, 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 and eventually blank. The blank could be used as an end marker. It will be only made of bits. So let me just remark that this way, the alphabet on which we measure program size is really binary. In the blank complexity setting, the head can hit and recognize the first blank after the program, which grants a third symbol in the alphabet of program. In the blank complexity setting, the head can hit and recognize the first blank after the program. Which grants a third symbol for the alphabet of programs. Which grants a third symbol for the alphabet of programs. And as a last remark that I want to do in this overview, before going to the formalization, is that real programming languages are self-delimited. We have instructions to say when a program starts and when a program ends. And as I discussed with Matteo, and perhaps Matteo you can expand on it, but if we don't have those instructions, it can be very messy for a computer because you can sort of launch the computer further in the computer's memory and no longer in what it's supposed to compute. I mentioned that in C, there's like those.
There is a sort of vulnerability that is called the buffer overflow. When,
Buffer overflow?
This is the most common that happens. And this is due to the fact that some programs does not check how the size of the data set, and in this way it's possible for sometimes to put some malicious code in the memory and try to move the pointer or the instruction pointer to my malicious code. In that way, when I execute a program with this vulnerability, also my malicious code will be executed.
Okay. So you can just send the pointer beyond where it's supposed to.
Yeah, then this is crucial for security.
Exactly, okay. Thanks. Real programming languages are self-delimiting. Because they provide instructions for beginning and ending programs. This allows for a program to be constructed by subroutines in a concatenated way or a nested way. You can just invoke a subroutine and then another subroutine, and you don't have to care about delimiters because each subroutine will be self-delimited. It knows when that subroutine is ending and when the next one is starting. This allows a program to be well formed by concatenating or nesting subprograms. Okay, let's see how this connects with, the language we've been building up, the one of Turing machines. They're called self-delimiting Turing machines. A self-delimiting Turing machine it's a long name. I tend to avoid acronyms, but for this one I think I will take one. SDTM. Self-delimiting Turing machines, because I'll have to write it again a few times. Has 3 tapes. That's a little tight. Has 3 tapes. In fact, let me draw it. There's the input tape. Input or program tape. So it contains a first blank. And let me do in blue the position of the pointer at the initial configuration. So initially it will have a pointer scanning a first blank. It is semi-infinite. It doesn't matter if we want to have it two-way infinite, but it's only moving one way, so there's one way which is useless. And then there are the bits of the program. P1, P2, P3, P4, P5, I don't know, P6, and so on. So that's the bits of the program. And yeah, it's called the input or the program tape. And it's one way. By which I mean it only has one move for its head, and it's to move right. And it's read only. It's never going to write something here. It leaves the string as is. So that's for the program or the input tape. The other tape is two-way infinite. It has a specific square on which the head starts. And yeah, maybe, you know, on usual computations, on resource-free computation, this tape is going to be free. It's going to be empty to start with. So it's the work tape. It's two ways. So this one can move left and right. And it's read and write. Okay, that was the input or the program tape. That's the work tape. What else can I say? I think I'll write it here. It may contain a string on it. It will be the auxiliary information string. It may contain a string y, just to make sure I'm complete in my exposition. When I'm writing a string like this, like y is y1, y2, y3, yn. I'm assuming y is an n-bit string. And what is y? It's the auxiliary information. Right? When we wanted a notion of conditional complexity, we needed a way to give to the machine also an extra string, which is like, may contain some patterns with x. But what we minimize to define the Kolmogorov complexity or the algorithmic complexity is the program string. Y will be like a fixed string. So again, to be consistent, y is going to start y1, y2, y3, yn. Like that. That's the work tape. And finally, we're also going to have the output tape. it's one-way infinite. The head starts again on the leftmost square, and it starts empty. In fact, the whole output tape string starts empty. Okay, so whatever resides here will be the programs. Whatever resides here will be the auxiliary information at the beginning of the computation. Now the auxiliary information might be preserved, it might be written over, that doesn't really matter. The Turing machine will make its computation now with 3 heads. So that means the fact that it has 3 heads, it means that its rules for deciding what it does next is a function of its internal state, but also on the 3 symbols that it is currently scanning. You're realizing that this symbol is always going to be informationless. So the output tape is not there to read anything. In fact, it's a write only. The read information is meaningless. So it's one way, write only. I was saying that the rules are given by basically what this one is reading and this one is reading. Now, each computation step might consist of one of the following actions. Move this to the right, never to the left. That could be an action. Okay, I'm ready to move my input tape head to the right. That could be an action. It could be write something here where you're currently pointing on the work tape. It could be a 0 or 1 or a blank. It can move this one left or right. Or it can also write something on the output tape and then move it automatically to the right. So whatever is being written on the output tape is fixed. Okay. Just if we want to speak of just plain complexity, technically I wouldn't really have needed the output tape. It's just useful if we want to get into monotone machines later. That's an apartheid. But it's good to just think of it this way. The computation is going there, and when my computer is ready, if you want, it could have printed X here, and then the final routine is to copy X downstairs. But we're going to define the output of the Turing machine as what resides on the output tape, naturally. Okay, I think I'll move upstairs here. Are there questions so far? Nope. Now let's consider a self-delimiting Turing machine T. Let T be a self-delimiting Turing machine. If, after finitely many steps, T halts, T with a few things. So yeah, the most crucial part is the program tape, the input tape. And this is what we're going to cover here with a string P that has been scanned on the input tape. So by what do I mean by has been scanned? This is how my machine starts. It will eventually move right, move right, move right, move right, do stuff, start computing X on the output tape, eventually halt, suppose with the head on P5. So what I define as the string P that has been scanned on the input tape is whatever is from P1 to P5. So I'm going to specify it. It's basically the head, when the computation halts, needs to be on the last bit of the program to call the string P that has been scanned the program for that computation. So a string P that has been scanned on the input tape, namely, or more precisely, upon halting, the head of the input tape is on the last bit of P. But no further. In fact, my favorite way to think of the input tape is that it contains no blanks. It's not even in the rules of the Turing machine for this head to read the blank, except perhaps for the first square, because we're having a special first square. It just cannot read a blank. It cannot cheat. It cannot go after P6 and say, oh, that's a blank. So my program is only 6-bit, so it's that string. So then I process in this way. If it would have been the first 5 bits of the program, I would have done something different, which might be the case in the plain complexity setting. Here I'm imposing that it moves to the right, it moves to the right, it moves to the right. You can think of it as just plenty of zeros and ones. And if it halts with scanning P5, well then what I define to be the program is going to be the string P1, P2, P3, P4, P5. So that actually is still an if. If after finitely many steps, T halt with, that was the most crucial one, and something else here that concerns the work tape, possibly a string Y that was initially given as auxiliary information on the work tape. And finally, a string X on the output tape. So if, there's many things, if T halts, its input tape has read some string P, no more. It possibly had the initial string Y as given on its work tape, and it halts by producing the string X on the output tape. In that case, and only in that case, we're going to say that then we say if, actually, lowercase t in fact, then we say that the computation is successful and t of p comma y equals x. You remember when we did the move of shifting from a one-tape Turing machine to a two-tape Turing machine? Now t was defined with having two entries. We did that precisely to take care of the auxiliary information. So here we have three tapes. So one might say, no, you need three entries. No, the output tape is always initially empty. So there's no such thing as something written on the output tape initially. So really we have a pair of strings to consider as input. One of them has to be understood as some fixed resource, y, and the other one will be the program tape. So we're looking over all possible programs to use y to possibly compute x. That will be the idea of complexity. So we say that the computation is successful. That's one thing. It's fun to be a successful computation. And we write this, maybe in particular, might write t of py down arrow. No h in arrow. Right, this just means that this is defined. Okay, otherwise, computation is successful is very fun, but computation is a failure. That's very bad. Bad name. The computation is a failure. And, well, t, p, y is not defined. Are there questions? Let's have a break and Davide. Yeah.
With that P, do you mean all the subroutines together? Like P1, P2, P3 all together?
Oh, sorry. Okay. I need to be clear. These were not subroutines. These were bits.
So every P is either or 0 or 1?
Yeah, P equals P1, P2, P3. In my example, P6 is a string of 6-bit. 6 bits. I will want, as you mentioned, to concatenate subroutines. I will typically write them as PQR. And like P is a subroutine that does this and that and that. Q is another one that does this and that and that. we have met these kinds of argument, right? When I proved the easy side of the chain rule, we had at some point, a program which was of the form RQ or RX star Q, something like that. I was concatenating them. We right away see we had a problem of delimiters in plane complexity. It will be nicely solved here because all subroutines are self-delimited. So when I write down RPQ, well, R does not need to bother about telling apart P and Q like we had in the problem of plane complexity. Sorry, I'm really in advance on myself. I should relax about it, and we will view that after the break, perhaps. Have a nice break and reconvene at past. Okay. Self-delimiting Turing machines can be effectively enumerated right? T1, T2, ... We have them all. They're all there, and they're all self-delimiting Turing machines. Again, same trick. By their rules, you write down their rules in a canonical way, and then you can shrink that if you want into a number, saying, oh, my first valid encoding of a Turing machine, my second valid encoding of a Turing machine defines respectively T1, T2, and so on. Brief reminder of what we did for Turing machines, but it's exactly the same thing. And what matters is that there exists U, well, let me write it down as a self-delimiting universal Turing machine. U, such that U of I bar P, no, I have I bar Q, but yeah, I bar Q is equal to Ti of Q for all I in Q. So same thing again. If U expects only one input, so here I'm implicitly putting the auxiliary information Y to the empty string. I'm disregarding auxiliary information. So U has a single input, but it interprets it as a pair of strings, I and Q, and it simulates Turing machine number I, or should I have said self-delimiting Turing machine number I on input Q. Exactly as before, that relation doesn't change. Yeah, so as I said, this is when Y is equal to the empty string, so perhaps more generally, U of I bar Q comma Y, that's what's written on the first tape, namely the program tape, and that's what's written on the work tape, which is also our auxiliary information tape, is equal to exactly what Ti would do if it was given program Q on work tape initialized with the string Y. For all I, Q, Y. Okay, so this is what's written on the input tape, input or program tape. And this is what is written on the work tape. This defines the order of them, of the strings.
Sorry.
Yes.
What do you mean with I bar?
Sure. I bar was one of our self-delimiting version of I. I bar was equal to, what was it, 0 or 1? 1 to the length of I, 0 I.
No, the encoding of the length of I. Like the encoding of the length of I after 1. After the 2.
This would be I prime, I think. I denoted.
I think that's how I remember I bar.
This is I prime. Right?
No, this is I bar. I prime is is more elaborated. I prime was 1 to the length.
Oh, the length of the length?
Yeah.
Is the double?
Length of the length of I. 0. Length of I. I. This was I prime.
Was inverted.
Yeah. Yeah.
But then why using I bar when we have I prime that is faster? I mean, it's better.
Yeah, I prime is more economical. You're right. For now, it doesn't matter.
Okay.
It fulfills the additive optimality, which we're going to see next, but it's exactly like what we had for plane complexity. I can't remember in which context, but I remember reading some papers by Vitani in which he specifically needed to define the universal Turing machine, but with the encoding with I prime. It doesn't come back to my mind when and how and why. Maybe later in the course we'll see when and why and why. But you know, we've met those two candidates. For my purposes now, I'm happy with I bar. It works. So Davide, to come back to your question, it's basically a way to encode I in a self-delimiting way. So now self-delimitation starts to make even more sense with those self-limiting Turing machines. You know, if I have a Turing machine which can only read from left to right, and it's given I bar, it can know what is I while having the head on the rightmost bit of I bar without overshooting. Right? If I give you just I like that, and us human beings were a bit like Turing machines, we can read I, and we can know unambiguously what is I, but we're cheating because we're like overflowing on the blank, and we're saying, oh, since there's a blank here, you know, like y, I suppose I is equal to 1, 1, 0, 1, 1. You go like, yeah, okay, 1, 1, 0, 1, 1. Oh, nothing here. Therefore, this is I. Right? We're overshooting. That's what I said. But here, you can say, okay, I will have 1 to the power of 5. So, in this case, I bar will be 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1. Why? Because it's 1 and encoded as many times as there are bits in I, in the length of I. The length of I is 5. So I've got 1, 1, 1, 1, 1. 5 times. I put a 0, and then I encode I as is. If I read this from left to right, well, I can read 1, and then, you know, on my work tape, do some calculations. 1, okay, at 2, 3, 4, 5. Okay, I need to read 5, because now I hit a 0. So I need to read the 5 next bit, and I stop. Then I know that I is precisely this one, and I don't overshoot. And that's why I mentioned earlier that this is a self-delimiting encoding of I. Okay. Other questions? Remark. Observe that for all self-delimiting Turing machines for all auxiliary information y, the set of programs that lead to a halting computation I should say the set of programs that lead to a successful computation namely this set, the set of p's such that t, p, y is defined is a prefix-free set. Okay, why? Well, take one valid program. That is one program that leads to a successful computation. Call it Q. If Q, well, if T of QY halts, or is a successful computation, it means that the last bit of Q has been read. And no more. Therefore, no program of the form QS for some non-empty string S can also lead to a successful computation. Right? In fact, let's think about it. What happens if QS sits on the program input initially, and then we start the computation for the Turing machine T? It's going to do its thing and read the first bits of Q and do its thing. And eventually it's going to read the last bit of Q. And then what? It halts. So it's not that QS is like complete nonsense, like for this Turing machine. It would actually do something, but Q would qualify to be the program. Because by our definition of what the program was, it was what had been read by the head, and which is scanning the last tape. Okay, so another way to understand it is that if Q is a valid program for a self-delimiting Turing machine, then any infinite bit string that starts with Q will sort of lead the same computation, because the Turing machine will read and do its thing. Eventually it will read the whole of Q and halt. And the rest is, well, doesn't qualify to be a program because we say Q is the program in that case. But still, via our definition, we would still demand that, technically speaking, in that case here, T of QS would still return non-defined. Because we chose that a successful computation is defined with respect to the program, in this case Q, the shortest prefix, which works. Okay, so this is just a way to, just to think about it. It's basically going to stop on Q, so Q is our program. And what I needed, in fact, for this argument is that I don't want another valid program of the form QS. Well, that's fine, because my head is going to stop at Q and the computation is going to halt. So the program really is Q. So that's a prefix-free set. In particular,
Sorry, can I interrupt real quick?
Please, please.
I think I didn't quite understand. So when we say the computation is a failure, it's because, so if you have Q and then S tacked on, we say it's a failure because it halts on Q, but it's supposed to read QS.
yeah,
I mean, I'm confused about it, because the up arrow to me means it doesn't halt.
That's
then,
what
then it should halt on Q, right? So,
yeah, I'm just going to use it now as it's undefined. Because what is defined is T of Q halts.
Yeah.
And to deserve this symbol, all of these criteria need to be fulfilled. Now here Y, in our example, Y was the empty string, so we can dismiss Y. But really the criteria is that a string P that has been scanned on the input tape, the computation is successful if, after finitely many steps, T halts with the string P that has been scanned on the input tape, and no more than P. So QS does not qualify.
Because it didn't finish reading the input.
Exactly.
Okay.
It only qualifies for Q.
It sort of scanned part of its input and then halted early.
Yeah.
So, okay.
In fact, if you give QS, so what I said is that if I give QS to the prefix machine, it's going to say, thanks, you've given me the program Q, and I've halted. It's not going to overshoot and read S anyways. It's self-delimiting. So in that case, we're going to say, oh, well, the program was Q. Because we're after lengths of program.
Mm-hmm.
Yeah, the S part is not even read.
Okay.
Thanks for the questions. I really encourage questions, right? Please always be free.
Does the machine, so I want to understand the halting of the machine. Does the machine necessarily halt when it reaches the last symbol, or even after it reaches the last symbol it could continue operating on the work tape for some amount of time?
It can loop.
It
can loop.
It can loop, right? Yeah. So you could write programs where it reads the program tape, it copies it on the work tape, and now on the work tape it operates bidirectionally.
Yes, it can do that.
It can do that.
Yeah. If that's useful, in some cases it will be. Y could be a piece of software. Y could be a valid program. And so P could be a very short program which basically says, just read what's on your work tape. Everything is there, and then Y will contain the information. We're going to see examples. Yeah. Good. they're not really easy definitions and notions. This course is a bit, sometimes, it took me time to make peace with prefix complexity and appreciate it. So don't worry if it's not supernatural. Okay, so we said that this is a prefix free set. One of them that's going to come up often, in particular, the set of p's such that u of p halts is a prefix free set. And it's just a special case of this general set here. Good. So with this in hand, we can revisit our definitions of algorithmic complexity. And I will go a bit faster, because you remember when we did plain complexity, I wrote down C of x, the definition of C of x, the complexity of a single string x. And then we had C of a pair of string x and y, and I basically rewrote the whole definition just to realize it was the same thing, but encoding the pair xy. And then at the end, we had the definition of the conditional complexity. And after the conditional complexity, I had to re-update, if you remember correctly, I had to re-update what I mean then by C of x when the machine has two tastes finally. So now I'm going straight to the conditional complexity. The conditional prefix algorithmic complexity k of xy, k of x given y of a string x with auxiliary information y is k of x given y is the minimum over all programs of the length of that program, such that u of p comma y equals x, where u is our is this machine here. It's our self-delimiting universal Turing machine. So it's the length of the shortest program which can produce the string x, in this case, possibly with auxiliary information y. However, the program needs to be self-delimited. Okay, as in plain complexity, we're not going to redo the proof, it's exactly the same as in plain complexity. U is additively optimal and the invariance theorem holds. Which means for all self-delimiting Turing machines T, and for all x and y strings, k of x given y, which is the same as, I've already put the shortcut, but it's the Kolmogorov, well, algorithmic complexity with respect to the machine U, right? Exactly in the same scenario that we've seen with plane complexity. This notion is defined with respect to a reference Turing machine, with respect to a reference universal self-delimiting Turing machine U. We used to put the label U here. And then precisely because of the invariance theorem, we could remove the label U. So now I'm just re-putting it for the sake of stating the invariance theorem. K without a U, which is implied to be K with the U of x given y, is smaller or equal to K T of x given y plus O of 1. This was the invariance theorem. Is that if you see a complexity measure for each Turing machine T, you're having many such functions here, but the complexity measure with respect to U is minimal, in the sense that it is upper bounded by all others up to a constant. Are there questions? I omit the proof. Really just check again for plane complexity and you realize that it works. It works not just because the set of valid programs for U is a prefix-free set, but also because all Turing machines that are involved are such that the set of their valid programs is also a prefix-free set. It could be a problem sheet question. I'll see. It's very analogous. It's almost two. It's really the same. Yeah. Okay. The unconditional complexity, well, unconditional prefix complexity is k of x. We're just going to write x, and that is by definition k of x given the empty string epsilon. And, oh yeah, that's one thing. X star is the shortest program. for U to compute X. Again. Do you remember if there's many shortest programs? What we do? How do we define X star?
The one that is like fast, the lowest time complexity.
Smallest time, yeah, the fastest one, or the one that computes X in the least amount of computational steps. Next course we'll see where that comes in. Have that in mind. But so far it's same as before. And finally the prefix complexity of a pair. K of X comma Y. That's just shorthand for K of X, well, the encoding of X and Y. So, again, to define the complexity of a pair, we need to fix an encoding. There's various favorite ways one can choose as encoding. Fix one, and the prefix complexity of a pair is defined this way. Are there questions? So we're almost where we were, I think, in terms of definitions of things of notions related to algorithmic complexity. By which I mean where we were with plane complexity. We could define the complexity, the plane complexity, the prefix complexity of a pair, prefix complexity of a single object. Well, both of these notions rely on the conditional prefix complexity, this one here, which relies on a definition of a machine U, which can universal machine which can simulate all other self-delimiting Turing machines. At this stage, I would like to revisit the problems that we've seen last time. I think today I could do maybe one or two of those problems and see where, well, to see that prefix complexity solves them. Are there questions before I proceed? Okay, revisiting the problems or solutions to the problems. With plane complexity. We'll do them in reverse order. So I start with the problem number 4, which is the problem that I presented at the beginning of this class. 4. The code, right, I called it SP for shortest program, which is a code for finite bit strings into finite bit strings. Right, and the natural code is to map X to X star, its shortest program. Now, X star understood in terms of the setting of prefix complexity. Well, this code is a prefix code. Now it is. Well, why? Because this, the set of programs for you is a prefix code. So many of those programs are not the shortest program for some string. But now I'm basically mapping all strings to their shortest program. So just to remind you, a prefix code was that we needed this set of code words to be a prefix-free set, to be such that no code word is the prefix of another code word. Now the set of all code words is the set of all x stars for all x, namely the set of all programs that happen to be the shortest program for a string x. Well, that is a subset of the set of all programs. And that is a prefix-free set. And therefore, the set of code words here, which are all shortest programs, is also a prefix-free set. I see question marks in many eyes.
The programs are prefix free by definition, basically, or
Okay, I should expand a bit more on the remark.
because we define them as leading to successful computations, and prefix free was kind of built into that.
Yeah. So if Q is a valid is a valid program, namely a program which leads to a successful computation, it means that the scanner, the head on the input tape, has read all of Q but no more.
Yeah.
And so if I consider a program of the form Q and then something else, this cannot be a valid program because we defined a valid program or a successful computation with the program Q to be where the head stops. This was in the 3 points that I wrote. And so QS was not a program which leads to a successful computation. As I said, I had written it there in blue, but I mentioned that in our definition, T of QS would be undefined. And you mentioned, Will, you said like, we were used to see this symbol when the programs were looping. So there's now different ways, or 2 different ways to write this now. If you see T of something up arrow, it might be that the something is in fact a valid program. The head will never read beyond that input, but it's executing a loop, an infinite loop, and so it will never halt. I will write that. But it could also be that, well, it happens that this string here is not a valid program. By valid program, I mean that the reading head is stopping at Q and is never reaching into the bits of S. In our example, this would hold, but also, by assumption, this holds.
So the fact that our shortest program code is prefix code is ultimately just because of the redefinition from Turing machines to self-delimiting Turing machines?
Exactly.
Basically?
Yeah.
Okay.
On a self-delimiting universal computer, the set of all programs that halt is such that no program that halt is the prefix of another program that halt.
So we restricted ourselves to a subset of what we had before. Before we just had all Turing machines.
Mm-hmm.
And now we say we only are interested in the self-delimiting ones.
Correct. Yeah.
Which is fine because that's sufficient to compute every computable function.
Yeah.
Okay.
Yeah. The big motivations again was to avoid the sort of cheat that we have when we in fact measure program size in a ternary alphabet, because by allowing our program to possibly, or our computer or Turing machine to possibly overshoot, well, the program is not encoding within itself the length. So we're measuring the length of something, which in fact the alphabet was 0, 1, and blank. Here, we're imposing that the input tape contains only zeros and ones. And so the program cannot hope to hit a blank. And so it needs to know within itself, oh, Q is until here, and then I halt to have a successful computation.
Yeah, right. We're trying to kind of, we're tightening the screws. We're removing all the ways that you could cheat.
Exactly, yeah.
Inaccuracies around the edges kind of thing.
We have to play a little bit with it and revisit some arguments that we're going to see, and I'm about to do one. So yeah, let me just be a bit more clear.
Sorry, is it possible to have a valid to the machine in this sense, so it actually reads all the input string, but never adds because loops at the end? So I read the program, and the program says loop. How can I express this in that kind of way?
Yeah, okay. So suppose you're really coding a program that is looping. Call this program P. Or you're just going to write that U of P does not produce an output. It loops. This is because of you made it loop. P was a loop. So in fact, what might happen in that self-delimiting universal computation is that it's going to read the first bit of the program, the second bit of the program, and the head is going to go until the last bit of the program. So it seems like it fulfills the first criterion, like it's really reading the last bit of P. P was self-delimiting. You did a good job. Your program was self-delimiting, but it was a loop, so it will never halt. Remember in the condition I said, if T halts and on its input tape it has P, on its work tape it has Y, and on its output tape it produces X, then we say that T of P comma Y equals X, and that T is a successful computation. So in this case, you sort of made it syntactically correct program, self-delimiting, but you made a loop. Another way to get this symbol is to have, as I said, U of Q halts. It computes the empty string, whatever. And then
P equals QS.
I'm like, yeah, what about Q0110? Well, by our definitions, we're going to write this. U of Q0110 is undefined. I mentioned that still it would not, the universal Turing machine would not understand this as nonsense. Like if really its input tape is of the form, right, it has 3 tapes. That's the input tape, that's the work tape, and that's the output tape. And here it has a blank, and here it has Q1, Q2, Q3, Qn, the last bit of Q. And then it has 0, 1, 1, 0. Well, what is it going to do? It's going to start with its head here. It's going to do its thing. It's going to compute. It's going to move its head. Once it's going to get its head here, it's going to compute. And it's going to compute, I said the empty string, but let's make it interesting. U of Q computes 0, 0. So it computes 0, 0. It has its output tape head here. The work tape, I don't mind. So you want to say, oh, Charles, but we've given it Q and some extra bits, and it still carried some computation. Granted, it did carry some computation. This is something I've been repeating so far. But the computation that it has done is not Q0110. The computation that it has done is Q.
So the thing is that actually in a first attempt I just see if the computation halts and then see in which condition it halts actually. So if I read all the program, it is okay. If I have an output that is valid, it's okay, and that's all.
Mm-hmm.
So I first check of the ending computation, and then I see if the conditions are matched.
Yeah.
So northeast arrow has two meanings. First meaning, Turing machine just does not add, and that's it. Or I have not read all the input.
Yeah.
Okay.
Yeah. It could be because it's a prefix as halted, and so you will never ever reach this bit.
So if it halts, actually, it means that it halts
And is scanning the rightmost square. Exactly. These are very important questions. You have 2 days to think about more questions, and please bombard me on Thursday with some more questions. So, I don't know, I think I'm overshooting. I'm not a self-delimiting program. Yeah. Let's finish here.